the domain of the function. Well, you know all the guidelines to find the domain for rational functions. Set the denominator equals 0, solve the equation. Those are the values that give an undefined function. Those are the values that get out of the domain. And in some cases, those values represent vertical asymptotes or holes, well, depending on how the function behaves. We look at the intercepts, and well, if the equation, the function, it's too complicated to solve, well, you can omit. But for the examples that I have here, we're actually going to find all of them. All right, and the 2 points to find the intercept. But to find the x-intercept, you say y equals to 0, solve for x. To get the x-intercept, set y equals to 0, solve for x. You're going to do that in practice. Symmetry. Symmetry is something that we reviewed at the beginning of the semester in the review chapter. You might remember that part. So, I have the definitions again. F of negative x equals x. That's going to give us an even function. How about we highlight this? So when we have this condition to be true, that is, change the sign of the x in the given function, and if the output is the original function, then you have an even function. But otherwise, if you change the sign of x in the given function, and your output is the opposite in sign of the negative of the original function, then we have an odd function. And graphically, let's recall that an even function is a function that is symmetric about the y-axis, while an odd function is a function that is symmetric about the origin. So that's why we get the negative, Number 4, asymptotes. Horizontal asymptotes, vertical asymptotes, and slant asymptotes, all right? Well, so horizontal asymptotes, that we can relate that to chapter 2, limits. Limits at infinity for horizontal asymptote. Vertical asymptotes, well, the vertical asymptotes are going to be highly related to the domain. Whenever we have some restricted values, that is, some values of x that make the denominator 0, most likely those values of x represent vertical asymptote. Not always, right? But most of the times. And then slant asymptotes. We get a slant asymptote whenever we have polynomial over polynomial, and in this case the degree of the numerator is actually higher than that of higher by at least 1 unit than the degree in the denominator. What do we have to do in that situation? Polynomial long division. We're going to look at the quotient. That quotient will be the slant asymptote, and just screw the remaining terms. All right, we will look at one of those examples in which we'll have a slant asymptote. And well, steps 5 through 8, intervals of increase decrease. Based on that, we locate any max and mins, intervals of concavity, and points of inflection, and in the end, just sketch the curve with all that information. All right, so let's go about some examples. Good thing we're going to spend 2 whole lectures looking at many examples about this. So number 1, let's analyze the function ln of x squared plus 6. All right, number 1, let's find the domain of the function. It's a logarithmic function. You want to find out the values that make this function undefined. In other words, you want to set, in this case, x squared plus 6. You might want to set it greater than 0. That's the condition for the OK values of the natural log. Very similar to the radical functions of even index, in which we set the radicand greater than or equal. For logarithmics, we set it just greater than 0. Well, in this case, you might want not even bothering solving the inequality, because, well, x squared, what is that going to output regardless of negative or positive? Isn't that going to output a positive? On top of that, at 6, it's going to make it more positive. Any positive value will always be greater than 0. So in this case, this inequality, true for all x. That means the domain will be all real numbers, negative infinity to positive infinity. All right? I mean, just try to solve the inequality. X squared greater than negative 6. Okay, take the square root here. X greater than plus or minus negative or root of negative 6. Well, that's an imaginary number. We're looking for real values, not imaginary values. So in this case, that inequality is true for all x, right? X-intercept. So for x-intercept, well, let me write it down. Set y equals to 0, set x equals to 0 for the y-intercept. So that means, well, f of x ultimately equals to y. So that's a 0 equals ln of x squared plus 6. And in this case, exponentiate both sides to get rid of the ln. That's going to give us x squared plus 6 equals e to the 0, which is 1. X squared equals to 1 minus 6, which is negative 5. But again, x equals plus or minus square root of negative 5. Isn't that again imaginary numbers? But we're looking for real numbers only. So just cross this out and just mention no x-intercept. Let's see if it's the same for the y-intercept. For the y-intercept, set x equals to 0 and simplify for y. So y equals to ln of 0 squared plus 6. Well, y equals ln of 0 squared plus 6. That's simply the ln, the natural log of 6. Alright? And well, let's leave it like this, or maybe, let me see if I have my calculator to simplify the values, so at least we get an idea of what these values are. Alright. So yes, we're not going to use the calculator to graph the function, but we can use it to calculate some of the values, okay? So that ln of 6, that equals to y approximately 1.7917. That is, well, be careful to write x-intercepts and y-intercepts as order pairs, not just values. That means this is x equals to 0, comma, roughly 1.7917. Alright? Symmetry. For symmetry, let's check f of negative x and see what we get. So f of negative x equals ln of negative x quantity squared plus 6. Notice we're shifting the x with negative x. However, what's going to happen? Negative x quantity squared, isn't that just going to be ln of x squared plus 6? But in this case, what is this? Isn't that the original function f of x? What is this going to tell us? Well, since we get, or rather we got the same function, this is symmetric. About the y-axis. In other words, is even. It's an even function. Alright? So we have some information already about, well, we have only one intercept. We have the symmetry. We got the domain. Well, asymptotes. Let's check if we have asymptotes. Well, we will definitely not going to have any asymptotes. So number one, no horizontal asymptotes, number one, because, well, if you take the limit of ln of x squared plus 6, that's how we get horizontal asymptotes. At infinity, well, ln of infinity always goes to infinity, so this one doesn't have any horizontal asymptotes. And the reason why it doesn't have any vertical asymptotes, it's because this time we don't have any denominators that made the function undefined. Those are again related to vertical asymptotes, so really no asymptotes, not applicable in this case. All right. Derivative test. So let's get to the calculus and get the intervals in which the function increases and decreases. First derivative test. So number one, let's take f prime. So again, we have the function here. Find the first derivative, f prime of x. That's the derivative of a logarithmic function is always 1 divided by the quantity inside of the parentheses or the absolute value bars of the logarithmic function, that is 1 over x squared plus 6, and by minute chain rule that times the derivative of the quantity inside of parentheses. What's the derivative of that? 2x, all right? So times 2x. Simplifying this to a single quotient. All right, so we got the derivative. And well, what do we need to do in order to get those intervals in which the function increases or decreases? So we have to set the derivative equal to 0 to find the critical values. All right, so let's set 2x over x squared plus 6 equal to 0 and solve for x, because in this case we have a quotient. We need to set both the numerator, that is the values, to get the values that make the derivative 0, or undefined, that is the denominator equal to 0. Those are going to be our critical values. All right, so let's set on the one hand 2x equal to 0, and x squared plus 6 equal to 0. Well, divide both sides by 2. X equals to 0 is one critical value, and over here x squared equals to negative 6. But again, is it possible to square a number and get a negative number out of it? Well, so that's essentially saying plus or minus the square root of negative 6, which is going to be an imaginary number. But in this case, we don't care about imaginaries or complex values. We just want real values. So no critical values out of the denominator, on the numerator. And in this case, that we are going to have only one single, only one critical value. So let's see. So one critical value which we will plot in the real number line, and that critical value is 0. So in the same way that we did a couple of sections ago, this critical value will give us two intervals to test the increasing, decreasing, or the behavior of the derivative of the function. And well, that first interval will be defined by negative infinity to 0, and 0 to infinity for the second interval. Alright, so from here we need to check some test values. So let's pick our favorite test value, less than 0. How about negative 1? What about 1 for the other interval? So don't pick the most complicated value. Well, in some cases we would have to select a complicated value that once plugged in simplifies the calculation. We may get to see something like this. You'll see later. So, well, let's test x equals negative 1 and test x equals to 1. And again, where do we test these test values?
The 2x over the x.
It's going to be in the derivative, right? In f prime of x, all right? So, number 1. So, f prime at negative 1, that's 2 times negative 1 over negative 1 squared plus 6. That's negative 2 over 7. That's a number less than 0. That means it's negative. The derivative is negative at that value of x. For x equals to 1, f prime. So that's 2 times 1 over 1 squared plus 6. So that's 2 over 7. That's a positive value. What is that going to mean?
Concave down, concave up.
So decreasing, decreasing. and increasing.
So when is it the concave up and down? Is that when it's just the, not the inverse of the prime of x?
No, that's when we do the second derivative, when we get the hypercritical values. So this means we're going to get the following. So we're going to get a decreasing and then an increasing. What is that going to mean? Are we going to have a relative maximum or a relative minimum? Minimum. And well, even if you get a change between decreasing, increasing, or increasing to decreasing, this critical value may even not be in the domain of the original function, as one of the examples that we did back in that section. But again, the domain of this function is all real numbers, so this will for sure be a legitimate relative maximum, all right? So relative maximum at x equals to 0. So no relative minimum. NA. Rel max. Oh, wait. No, it's rel min. Yeah, min. So rel max, not applicable. And in this case, these are in f of x, in the original function. That is f evaluated at the critical value 0, that's ln of 0 squared plus 6, that's ln of 6. We already evaluated that ln of 6, right? That's actually coincident with the y-intercept that we got from the previous page. So we're getting there, we're almost there. So let's look at everything related to the second derivative. In this case, that's the intervals in which the function will be concave up and concave down. And well, so number one, let's find the second derivative. So number one, the first derivative, let me write it down, f prime is 2x over x squared plus 6. So to find the second derivative, well, it looks like we need to use a special rule for this. What's that rule? Quotient rule. So that is u over v prime, that's u prime, v minus v prime u over the denominator squared. So let's find the derivative using the quotient rule. So see in this case how everything we have done about even the what's it called, the differentiation rules, we're gonna get different kinds of functions and whose derivatives are not even related to their original function. So f double prime, so that's the derivative of 2x, which is 2 times the denominator x plus 6 minus the derivative of the denominator, which is 2x, times 2x, which is the numerator, the whole thing divided by x squared plus 6 quantity squared. So just so you can see how this quotient rule works, that's a u prime v minus v prime u. Alright, and this is really the denominator squared, or rather v squared. So let's simplify. We'd better simplify the numerator here. So you don't want to set the second derivative equal to 0 while it's not yet simplified. Alright, and I believe I forgot a square here. Okay, so that's going to be f double prime of x equal to distribute the 2. That's a 2x squared plus 12 minus 4x squared. The whole thing divided by x squared plus 6 quantity squared. So we can simplify actually terms in the numerator. So we can go here. So that's 2x squared minus 4x squared. That's a negative 4x squared. Negative 4x squared plus 12. Divide that by x squared plus 6 quantity squared. And we're done simplifying. Yes?
Don't you mean it's -2, right?
Which one? Oh yeah, negative 2. Thank you. Negative 2. Thank you. So we may go about setting the derivative equal to 0. So that's negative 2x squared plus 12 over x squared plus 6 quantity squared. Set it equal to 0. And well, set the numerator. Well, actually this negative is only for the 2x squared, right? Negative 2x squared plus 12 equal to 0, and x squared plus 6 quantity squared equal to 0. Well, so for the second quantity, we'll take the square root on both sides. That's x squared plus 6 equal to 0. And we already saw this case, right? We don't get anything out of it because that's outputting imaginary numbers. So we don't want imaginary numbers, only real numbers. Solve this other equation. Negative 2x squared equals to negative 12. X squared equals to 6. And x equals plus or minus the square root of 6, which is fine. So how many critical numbers, or rather hypercritical numbers, again, we call critical numbers to the values that come from solving the derivative, and we call equal to 0, and we call hypercritical values to those values that come out of the second derivative equal to 0. So in this case, we will set, we have two results. Number one, negative root of 6, root of 6, those are our hypercritical values. And well, to get an idea of which test values to use, well, the square root of 6 equals roughly x equals plus or approximately plus or minus 2.45. all right, so that means, okay, let's set up the intervals. Negative infinity to negative root of 6, negative root of 6 to root of 6, root of 6 to positive infinity. Well, let's pick a test value. So any number less than negative root of 6, which is negative 2.45. How about negative 3? Positive 3 for the, because of symmetry, we can get the positive value. And the easiest value between negative root of 6 and root of 6 is 0. all right, so let's evaluate or test these two values. Oh, I need another test here. So that's test x equals to negative 3, x equals to 0, and x equals to 3. And again, where are we going to test these values on? The second derivative, right? In f double prime, not in the original, not in the first derivative, all right? Okay, so let's evaluate those. So what did we get for the second derivative? Okay, we got this madness here. Let me see if I can copy it. Oh, never mind. So that's going to be f double prime of negative 3, that's a negative 12 or negative 2x. Oops. Plus 12 over x squared plus 6 squared. Well, actually negative 3 squared. So negative 3 quantity squared, isn't that a positive 9? Positive 9 times negative 2, that's negative 18. Negative 18 plus 12, isn't that a negative 6? And well, negative 9 squared, that's 9. Plus 6 is 15. 15 squared, whatever that is, I don't care. Ultimately, what we care is that this is negative, isn't it? We really don't, because the value doesn't tell us anything. What tells us everything is only the sign. What about f double prime at 0? So that's negative 2 times 0 squared plus 12 over 0 squared plus 6, quantity squared. Well, 0 plus 12, that's 12 over 6 squared, which is 36. Doesn't matter, don't reduce. All I care is that this is positive. All right? And well, so test x equals to 3, f double prime at 0, that's 2 times 3 squared plus 12 over 3 squared, quantity squared, and actually negative here, and it's actually going to be the same, negative 6 over 15 squared, which again, no need to reduce. Just see that it is negative, it is less than 0. Alright? So let's say that this is negative, positive, negative. When it's negative, that means concave down, concave up, concave down. That means sad, happy, sad. Alright? So it's going concave down, concave up. Well, that means we are going to have 2 points of inflection, isn't it? One at negative root of 6, one other one at positive root of 6. And well, it looks like we have these points of inflection, and this we get them from f of x. All right, that is, we need to evaluate f at negative root of 6 and f evaluated at root of 6. So that's ln of negative root of 6, quantity squared plus 6, and ln of root of 6 squared plus 6. Well, in this case, negative squared becomes positive. Radical cancel, the power 2, that's a 6. 6 plus 6, that's 12. ln of 12. And same over here, ln of 12. Well, what's ln of 12? Just to get an idea of what it is. So ln of 12, that's 2.49. Well, put 2.48, yes. 2.48. 2.48. But in this case, these points should be stated as ordered pairs. So that's negative root of 6, ln of 12. Root of 6, ln of 12. Alright? So let's use all this information to sketch the graph of the function. Well, so how about we start by drawing a Cartesian plane. And I'm gonna go like negative 1, negative 2, negative 3, negative 4, just in case I need more values. So number 1, the domain of the function is all real numbers. That means we're not going to have any holes, no vertical asymptotes. Also, we're not going to have any horizontal asymptotes as well. So now, let's see. We have as an x-intercept the point 0 ln of 6, which is the point 0, 1.78, 1.8 roughly. All right. So that's one of the points. So 1.8, which is right here roughly. And well, what else do we have? We have that well, it's symmetric about the y-axis. Well, that's going to be seen once we get to the details to the remaining details. Now, asymptotes, first derivative test, that means we have a relative minimum at the point 0 ln of 6, which actually happens to be the y-intercept. That means that because we have a relative minimum, the graph should look like this. The shape of the graph is going to look like this at this point, right? What's going to happen on the other endpoint? Well, we'll find out. We'll find out. Okay, so it might be too wide right here. Let's see, what else do we have? Any concavity? Okay, concavity is here in the second table at the values negative root of 6 and root of 6 respectively. Those values 2.45. So 2.45 roughly here and here. That means that at this point the graph changes from, go to the table, from concave down to concave up, and then from concave up to concave down. That is, it's gonna go, it's concave down, goes to concave up, and it's gonna go like this. All right, so I know it's kind of a weird graph. However, check this out. This is basically concave out, concave down right here, right? And it's also concave down right here. But over here, it's concave up. Does that check with the results that we got from the second derivative test and the table as well? All right. And that's the minimum value, of course. And I think this is a good sketch for ultimately, I mean, we don't have to come up with the best and most precise graph. I mean, as long as it shows the actual values, you know, like the points of inflection roughly, and which is negative root of 6 ln of 12, root of 6 ln of 12, and the minimum value, which is actually the y-intercept. This is good enough. All right, just make sure to make it as good as possible and as consistent as possible with the results that we got from the calculus, right? The first derivative test, second derivative test, etc. All right. It's kind of a long problem because in this case we go over pretty much everything. We put everything together. Let's go over another example. Although we may not get the whole thing, but at least we're gonna get something. Analyze the curve y equals to x squared over x squared plus x squared minus 1. Number one, the domain. So for the domain, well, notice in this case this is a rational function. And for rational functions, you want the denominator. You want to set the denominator equal to 0, because that's going to tell us the values that make the function undefined. And in this case, those values will be linked to our vertical asymptotes. So x squared minus 1, set it equal to 0. That's x plus 1 times x minus 1, factoring the difference of squares, and from here x equals negative 1 and x equals to 1. So these are the values that make the function undefined. If we draw this in the number line, we express these values with open bubbles, because we don't want to plug in these values to it. And we need to express this result both in set notation x, such that x cannot be negative 1 and x cannot be 1. And using interval notation, the domain is negative infinity to negative 1, union negative 1 to 1, union 1 to infinity. That's all. Both notation. It's important to get used to both notations, because on the exam or on a quiz or on an activity, you may be asked for either one or both, actually. So that's the domain. X-intercepts. And again, to get the x-intercepts, set y equal to 0 and set x equals to 0. So set y equals to 0, that is, set the function equal to 0 to x squared over x squared minus 1 equal to 0. If you want to multiply both sides by x squared minus 1, that's basically x squared minus 1 times 0, which is going to be 0. So that's going to leave us with 2x equal to 0 and x equals 0. That's the only x-intercept. Well, but again, be careful, because that's only the x value. We need to express intercepts as order pairs, 0, 0. Any y-intercepts, let's see if we have them. So that is f of 0, that's 2 times 0 squared over 0 squared minus 1, that's equal to 0. Alright? 0 squared equals 0 times 2, that's 0. 0 squared minus 1 is negative 1, but 0 divided by negative 1, that's 0. And that's again as order pair, 0, 0. And in fact, this point, 0, 0, is both an x-intercept and a y-intercept. I mean, that's where the two axes cross, the x-axis and the y-axis. Symmetry. For symmetry, we have to check f of negative x. And if we get the original function, then it's even. It's an even function or symmetric about the y-axis. Otherwise, if we get the opposite, that is negative f of x, that's a function that is symmetric about the origin. In other words, it's an odd function. So let's evaluate f of negative x. Negative x squared, or rather 2 times over negative x quantity squared minus 1. Well, negative x squared, it's going to be 2x squared. Negative x squared, positive x squared minus 1. Well, in this case, we got the original function again, isn't it? We didn't get the opposite, nor we got anything weird, anything different. So in this case, this is equal to the original f of x. Therefore, even or and symmetric about the y-axis. So very similar to the previous example. All right, it's a symmetric, so we can get an idea that about the critical values that we're going to get. Most likely we're going to get the same critical value, positive and negative. That will give us some kind of a symmetric behavior here. Asymptotes from domain. This function has vertical asymptotes x equals -1 and x equals to 1. Now, what about horizontal asymptotes? Horizontal asymptotes, we get the limit of 2x squared over x squared minus 1. X approaches infinity. Or just observe the function. Notice the degree in the numerator and the denominator, they're both the same. So ultimately the limit will be y equals to 2. So the horizontal asymptote will be y equals to 1. Alright. Well, slant asymptotes, not applicable in this case because the degree in the numerator has to be higher at least by 1 degree than in the denominator.
Why is the horizontal?
Which one?
Why is the horizontal 1?
Because that's supposed to be a 2. Thank you. Yes. So we got the asymptotes. Okay, first derivative test. Hopefully we get through the first derivative test. So let's find the derivative of this function using the quotient rule. That is f prime of x equals to, okay, the derivative of the numerator, which is 4x times the denominator x squared minus 1, minus the derivative of the denominator, which is 2x times 2x squared, whole thing divided by the denominator squared. Well, let's simplify the derivative. You don't want to set the derivative this early. Simplify it as much as possible so you don't get a complicated equation to solve. So number 1, 4x times x squared, that's going to give us a 4x cubed minus 4x minus 4x cubed. And the good thing, check how this function is going to simplify a lot. We're gonna get a really nice function to work with. So this is equal to, okay, cancel 4x cubed with negative 4x cubed, and that's a negative 4x divided by x squared minus 1 quantity squared. So now that we have the derivative all the way, simplified all the way, we may set it equal to 0. So that's what I'm going to do. I'm going to continue up here. Negative 4x over x squared minus 1 is equal to 0. That means either negative 4x equal to 0 or x squared minus 1 squared equal to 0. Okay, the first equation is just a baby equation. I mean, divide both sides by negative 4. That's going to give us an x equal to 0. However, the second equation, take the square root to cancel the square. No need to show all. Show it if you want. Cancel, cancel. That's x squared minus 1 equal to 0. And well, in the previous step, I used the difference of squares. You can use the square root property to get the two other, yes.
Why do we have to take the, why do we have to set the denominator 0 if it would give it 100?
Because even though, that's a good question, so even though those points are not defining the original function, we are still supposed to study what's going on in their surroundings. I mean, like before that point, is it increasing or decreasing before that point, or increasing, decreasing after that point? So, yes.
So if we set the denominator 0 and then it gives a specific value, is that value a different value?
Yeah, so those are going to be additional critical values. So and again, even though these values x minus 1 and plus 1 are not in the domain, we can still, again, check whether it's increasing or decreasing at those values. So that's -1, 0, and 1. All right. So let's at least define the intervals. Well, so that's a negative infinity to -1, -1 to 0, 0 to 1, 1 to infinity. Let's get our test values. How about -2, -1/2, or -0.5? Decimals are fine. 0.5 and 2. Yes, in some cases there's no way around. We will have to work with either decimals or fractions. All right. Well, so do we have time? Yes. Let me list them. Oh my God, I needed additional. Well, I'm gonna do them over here. So test -2, test -0.5, test x equals to 0.5 and 2.